This video, we are going to have a practice on OpAmp, and we will try to have a detailed learning on it and discuss a lot on this. Like when we see the OpAmp picture, it's look like this. Here the terminal is V0 and we have a plus and minus over here, and this is V1 and somebody say this is V2. And we say that V0 is equal to A times of V1 minus V2. This is what the picture look like. However, if I draw the ideally what is the OpAmp's picture is, the terminals which is say V1, this is actually V plus, which is connected with a very high resistance and with a terminal called V minus. So this V minus is also a potential with respect to a virtual ground. So let us say this is a virtual ground. With respect to the virtual ground, this V minus is a potential with respect to virtual ground. Or let me just add it all. And V plus is also the potential with respect to the ground. And this resistance is called Ri, which is assumed to be very high, and that this terminal is plus and minus. If this terminal plus and minus, the potential over here is VE, and on the output side there is a R0 or resistance which is very low, and there is a dependent voltage source which is also connected to the ground over here, and this dependent voltage source will be called as A into VE, A times of the voltage across this Ri, and the terminal this will be called V0, which is the potential of this node with respect to ground. So this is all is about. But when we see the picture over here, so what we did, we just make this entire thing out of this picture. We just take it out, and what is available with us is this is 1, and another is this 2. So we have got this 1, this is 2, and this is 3. This is the third terminal over here what we have. And so rest of the things are like it is hidden inside, and we get a very simple circuit, and we can say it like this is grounded. And yes, in some of the book you have seen that this is VCC and this is VEE is written. So these are also written on that. Okay, VCC and VE, and maybe grounded. So we will try to do some numericals based on this logic. So let us start. So in this let's take one example. Let us say this is first numerical where we are taking it, and let us say this is OpAmp, and we have a plus and minus terminal, and this side is V0. What we will do is we will give the supply over here like this, plus and minus. And this inverting terminal we will short with this V0, right? This much we will do, and we will see that what is the output voltage. So what is the equivalent of that? So let us, this is Vs. Suppose this is the network, and what is the V0 in terms of Vs? That is the what is it we are interested to see, and then we will conclude that what it is. The non-inverting terminal is shorted with the output. It's like a feedback, and this side is a Vs, And if an electronic engineer will say, he will simply say V0 is equal to Vs, and he will say this is a unity follower. But we need to know that how is it possible. So we have got an equivalent circuit here, Ri, and this one is connected with plus minus Vs and then grounded, and this terminal, which is, you see that, so let me see, mark here 1, 2, and this is 3. So 1 is here, 2 is here, and the 3 is over here. You have got this dependent voltage source. This is your R0. So what you are doing is that you are actually connecting this wire and from here to here. So it will be good if I just draw in another one. So what you're doing is taking a wire from here, and this is what you are shorting it, like this wire. So this is the wire what you are going to short from 2 to 3 terminals. 2 to 3 terminals shorted. Now what is being asked to you is that what is the voltage here? So what is the V0? V0 is the terminal 3 and the ground, that is the voltage being asked. So, and here this is the VE, the voltage across this Ri, and here this is AV, is the voltage, dependent voltage source depend on. So from the picture, let us redraw the picture once again. This is Ri, let us say, with a plus minus, and this is V, and this is here my plus and minus Vs, and this is connected with R0, and here is my dependent voltage source, and this is what is grounded here, and this is here what is grounded. This is A times of VE, and what we want to know is that is V0 over here, the plus minus. So if this is a closed circuit, so I can write the KVL, Kirchhoff's voltage law, and if I write the equation, this equation will be written as here, that Vs, let the current is flowing in the direction like this is the current, and Vs plus Ri into I plus R0 into I plus AV is equals to 0. This is the, okay, 1 minus I left, minus of Vs, and in this way we can have we apply the KVL in this closed path. Then also we know that VE is equals to we can write the V in the small letter just because it's changing, right? This value is changing, so we can write V is equals to Ri into I. So we substitute the value of VE over here and then rewrite the equation from these two. We write here minus Vs. Okay, let me write quickly this one. So Ri and plus R0 plus, this is A times of Ri. This entire thing will be multiplied with I, right? This, and this. The three things I added written over here, and this is nothing but equal to Vs. So I can write here I is equal to Vs by R0 plus Ri 1 plus A. That is what the value of I. So what's the value of V0? The V0 is nothing but we can write V0 is equal to V0 is equal to R0 into I plus A times of V, and this is nothing but R0 by R0 into Vs. Put the value of I from here. So let me just write R0. What is the value of I? Is equal to Vs by R0 plus Ri 1 plus A plus A times of V, A times of what is V? V is the Ri into I, Ri into I, that's the value of, and I is again, we need to just put the value of I again. What is I is same Vs by R0 plus Ri 1 plus A. So at the bottom we have got the common terms. At the top we have got Vs, this is R0 plus ARI is the top. At the bottom we have R0 plus Ri 1 plus A. This is all we get. Now we know that the value of A is very high, much greater than 1. So what we will do is that we will say the V0 is equal to Vs. We will divide from top bottom both sides, we will divide by A like this. So on the bottom we will have R0 by A plus Ri 1 by A plus 1. Now when we divide any quantity with a very large number, so this number tends to 0, and this number also tends to 0, this term is also tends to 0. What is left out with it is Vs Ri by, here also Ri. So we left out with nothing, just simply these two terms will cancel out. So we can say V0 is equal to Vs, V0 is nearly equal to Vs, and what's the conclusion is that this is a unit follower, that V0 is equal to Vs. This is what is a conclusion. We derive a lot and get this answer, unit follower. Actually what happened is that Vs is the voltage at this node 1, and for ideal condition the voltage at node 2 is also Vs. And since the node 2 is connected with 3, the V0 is also Vs. That is why it is called unit follower. Let's take another example. This is a second example we'll take. Okay. Like here we will take the OpAmp, but this is plus and minus over here. This is V0. What we are going to do is we are just keeping it very simple. Like suppose here we give some resistance and we connect a potential over here. Right, this is okay. This is what we are getting. This is Vs, suppose. And this side is just we put at a ground, right? And we want to know what is the output voltage. And here what we did, we just take one feedback from the output and get it inside here. This is the R2 value and this one is R1, right? Now if this kind of circuit is there, you have got one terminal over here, this is terminal 2 and this side 3. So what is that? If we take it as an idle one, the terminal at 1 will be having a 0 potential. If it is idle, we will start writing that V plus is equal to V minus, and since this one terminal is grounded, so both are equal to 0. In ideal case, we have got this relation V plus is equal to V minus, and since V plus is 0, so V minus is also 0. So if this terminal number 2 is 0, so what we can have a very simple circuit like this, like okay, and we can represent it like this is having R1 and this is having the terminal with V minus equals to 0, and then we have got resistor R2 and this is the V0 we want to know, with having a plus and minus between these two terminals. So now this is also with respect to ground, we want to know what is V0. So this we can have a node at this point, and at this point node we can have node analysis, and we can say V minus, this side is Vs, V minus minus Vs by R1 is same as, or not same as, is plus V minus minus V0 by R2 is equal to 0. At this point KCL at this node, we have this equation. Since V minus is equal to 0, we can have Vs by R1 is equal to V0 by R2, and we can write here V0 is equal to minus of R2 by R1 into Vs. This is a very straight equation we get just because of one assumption, that V plus is equal to V minus. We get this straight answer. Now if we take the non-ideal case, so if we just remove this and we say let us have a non-ideal case, and what is the answers we are getting, right? So let's have that point of view. If a non-ideal case, so this circuit can be redrawn with Ri as a very high resistance Ri, and we have got this one terminal and two, and this is what VE, and here this terminal is grounded, and this terminal 1, 2 is connected with resistance R1, and then it is connected with plus minus Vs, and this side is grounded. The other side we have got R0 and a dependent source, that is AVE, and this one is also grounded, and what is shorted here is R2 is there, which is shorted, so this is what is taken out, and here it is R2 is there and it is there. So now this is V0 with respect to the ground, you have plus and minus, and this is your R2. Now this circuit is looking very ugly, and we need to just redraw it once more. So if we redraw it, it's like Ri we can mention over here, and we can mention here R1 with the plus minus as a voltage source Vs, and this is grounded, and this side is also, we can straight put it on the ground, and here we have got a resistance R2, and then we have got a resistance over here R0. Here we have got a circuit plus minus, that is dependent source, and that value is AVE. What is asked to us is what is the value of this V0 is being asked to us, right? This is the value which is asked to us, and now this circuit looks okay, good. So this side is the terminal voltage is V minus, and we can say this whatever potential across Re will be reflected in the dependent source. So we can apply the node analysis at this V minus node, and what we can get is V minus by R1 Ri plus V minus by minus Vs by R1 plus V minus and minus AVE divided by R2 plus R0 is equal to 0. This we got a simple straight line equation. And we substitute the value of V here. What is a V? So V is actually the terminal across this now. This is the value of V here. So I can write V is nothing but V minus of V minus, right? Minus of V minus. So this is the, and so since why? Because V is equal to Ri into I. So here my current direction assumed is downward, so this is minus, this is V minus is the potential between these 2 points, so V is equal to minus of that. So minus of V minus. So this is the potential of V minus is a term, it's just a nomenclature, right? V minus is a nomenclature, V plus is a nomenclature, 1, 2 terminal name. So V is equal to minus of V. So if I substitute the value of V as minus of Vi, so what I can do is I can just rewrite this. V minus is taken common and I can write Ri 1 by R1 plus this V is what? Minus of V minus. So I can take the V minus out and we can say 1 plus A and divided by R2 plus R0, this entire thing. And that is equals to Vs by R1. So this is what we get for V minus value. Okay, let us hold it over here that this is the value of V minus in terms of Vs, because this multiplication term will go denominator over here, it will get V minus. What is a V0? We are interested for V0. How much is a V0 over here? V0 is equals to V0 is equal to R0 and the current we can write like this, R0 into I is the current from this from this element, plus AVE, and V is again V minus of this. So let us rewrite this. So this will be nothing but R0I plus A. So instead of having plus, I can write minus of V minus. Okay, so V minus value is known to me, current is not known. Okay, so R0, what is the value of the current? Current is, this is what the current is. This is the value of I over here. Alright, so this current is how much? V minus plus A V minus by R2 plus R0. This is the value of current. Then we have got minus of A V minus. Right, so we have got like this, and we can rewrite this as, or we can take this Vi common from all. So if I take this Vi common from all, I am left out with R0 plus A times of R0 divided by R2 plus R0 minus of A. Right, we're taking the V minus common from all, and then what is the value of V0 here? V0 will be equals to V minus. If I normalize this will be R2 plus R0, R0 plus AR0 minus of AR2 minus of AR0, right? And here AR0 and we cancel out. What you left out with V minus into R0 minus AR2 by R2 plus R0. This is what we left out with. So if I substitute the value of V minus over here, I will get the value of V0 in terms of Vs. So I need a space over here. So what let's do, let us rub this part. Right, and let us put the value of V0, right? So we can write here V0 is equals to, this values we will substitute over here, R0 minus AR2 by R2 plus R0. This is one, and V minus values we will take it from here, Vs by R1 into 1 by Ri plus 1 by R1 plus 1 plus A by R2 plus R0. So this part, let us remove this. So we have done it correct. So So this is what the value of Vs by R1, 1 by Ra plus 1 by R1, 1 plus A by R2 plus R0. Okay, this is correct, right? So let us remove this part also. So we are not multiplying anywhere, just we are trying to keep everything as it is. The reason behind it is also there, that why we are keeping it. We are actually trying to put a limit term here, like we are going to normalize it by dividing A above and bottom like that. So here we have to write like okay, we will do it, but let me rewrite just once more. AR2 divided by R2 plus R0 into Vs into 1 by R1. I just multiply with everyone. R1 by Ri plus 1 plus 1 by, there is no need to multiply, so it's like we don't need to rewrite again also, it's not required. So what we are going to do is we are assuming here, this is the answer of V0 in terms of Vs. So we get our answer, but if we assume that A tends to infinite here and R0 tends to 0, if we take these two cases, so first we would take R0 equals to 0 here, like this is equal to 0, this is equal to 0, and here this is equal to 0. First let us rewrite this, A R2 by R2, so we get R2 also cancel out, so let us say minus of A. So minus of A into Vs by R1 into 1 by, and Ri is also tends to infinity, right? Ri is tends to infinity. You have got 1 plus 1 by R1 plus 1 plus A by R2. This is what I got here. So if A tends to infinity, so what we have to do is we have to multiply, this is a minus of Vs, divide this lower term with A, so 1 by A plus 1 by AR1 plus 1 by A plus 1 by R, this R2, this much we get. So here the 1 by A terms 0, this terms 0, this terms also get 0, 1 by A is there, so 1 by R2 is there. So R2 will go up, so what we will get here is V0 is equal to minus of Vs R2 by R1. This is what we are going to get. V0 is equal to minus of Vs R2 by R1. So we did a lot of exercise for non-idle OpAmp and get, this is the answer. This is what the answer of non-idle OpAmp, what is the value of V0 in terms of Vs, but this will be not there. This is one when we take R0 equals to 0. So this is the value of the non-idle OpAmp. And when we take this, these are the constants we will take, then we derive this in terms of very simple, and that is what it is said, that if this node terminal is 0, if this terminal is 0, voltage is 0, so this is assumed to be of 0 potential, so we can write the node analysis and we can get what is the voltage of V0 from this. Okay.